Hello YouTube, today I'll be making a quick tutorial on a topic that I believe is a natural extension of what I've covered in my previous tutorials, and this is called a segment tree. So we're going to be covering a similar problem that we did before when we talked about binary index trees. So this is a more, let's say, complex binary index tree or Fenwick tree, which is a really bad way to put it, but there is some overlap, and there are some cases where you can actually use a segment tree instead of a binary index tree. So I'm going to be giving you the overall intuition behind it, and we're covering a sample problem, and I'll show a little bit of source code that will give some insight into how this data structure works. So first of all, let's consider the good old problem of having an array, and we want to find the sum between any left and right within that array. So the nice thing is we want to have the properties that the query is O of log n and the update is O of log n. Okay? So we have these two specified. So with this being said, what is the overall idea of a segment tree? So let's look at the name for a second. So we see the name segment, and then we see tree. The idea is we break apart the array. So if we have an array with, let's say we have an array with 5 values, okay? We can have an array that's like 1, 2, 3, 4, 5. We can have one node like this, 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 and then we have different nodes here and different nodes here. So what we're going to have is essentially we're going to have segments. So we're going to say this upper node is elements 0 to 5. Now this upper node is elements 0 to 3. Now this node is 0 to 1. This one is actually this one's 0 to 2, sorry. And this one is 2 to 2. So what we're going to do is we're going to divide by 2 and round down. So this one is divided by 2, round up 1, 3 to 5. This one is going to be 5 to 5, 4 to 5, and this one is, naturally we're going to have children node down here, leaf nodes actually, that are going to be index 0, 1, let's do a different color, 0, 1, 2, 3, 4, and 5. Alright, so what are we actually doing here? We have different nodes, each one representing different segments. Now the idea of this is that whenever we do a change, we don't need to propagate it throughout all of the different nodes. We can only propagate the change throughout the segment that we're interested in. So let's cover a couple of basic ideas here. So first of all, one fact is that the height of this tree over here will be O of log n. Okay? Now why is that? Because the ranges are being divided every time. So if I have a range, let's say n, then it becomes n over 2, n over 4, so on until it gets to 1, which implies that we're going to have a O of log n bound on this height. Now the second aspect is how many nodes will there be? Well, at every single level, we're going to be adding, doing a summation for a height of log n of 2 to the I in worst case, which is 2 to the log n plus 1 minus 1 over 2 minus 1, which is 2 to the log n plus 1, which is 2 times 2 to the log n, which belongs to O of n. Okay, so we got, therefore, O of log n height O of n space So these are properties right now. So now let's cover what the actual time complexity will be for this operation. So if I want to find the summation from, let's say, 1 to 3, I'm going to start at this upper node, 0, 5, up here. And I'm going to say, okay, 1 to 3, I can't conclude anything from 0 to 5 because 1 to 3 is a subrange, so I'm going to recurse on both the left and the right. Now this is 0 to 2, so I need 1 to 3. So in this case, 0 to 2 doesn't encapsulate everything, so I'm going to have to recurse on 2 again. And then here I'm going to go to this node, and this node terminates. Similarly on the 3 to 5, I realized that I'm actually looking for, whoops, this is supposed to be a 3. I'm actually looking for 3 to 4. So I'm going to be going here, and then I'm going to go to this 3. So the main idea is that as you're hopping through these values, what you're going to notice is that we went from here to here, here to here, here to here, 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 here. The main idea is that at any point within the segment tree, we will really only perform a complete view. Hold on, actually this is 0 to 2. 0 to 2, 1 to 2. Yeah, we will only ever have at most 4 nodes within any specific level. Because in the case that we will only have 4 nodes traverse that at any specific level. Because assume for the sake of contradiction that we have 5. This means that we potentially had a node that looks like this. Let's assume the binary tree is this. Okay. So this is the binary search tree. If we have 5, then in that case we're going to have some sort of arrangement where there are 5 nodes selected like this. In the case that there's 5 nodes selected, first of all, we need to show that it cannot be contiguous. So in the case that it's contiguous, we would have 2 nodes side by side in addition to another node. So this means that we would have gone here, chosen to go on both paths, and then this one wasn't satisfied, so it had to go on both again. Then there was also one that was less than it. Well, we also had numbers that were larger in range. This means that all the values within this range were encapsulated by the fact that we selected a number that was also smaller and also a number that was larger than this parent over here. So you need to grasp this a little bit, but afterwards you'll realize that there's actually an upper bound of 4 nodes per level. And if there's an upper bound of 4 nodes per level, then we just simply get 4 of O of log n, which implies O of log n for every single query. And we do the exact same operation for the update. We will observe that there will only be at most 4 items, and for that reason, we're going to actually have a O log n update time as well. So how do you actually construct this tree? The way to construct this tree is that you have an array, and then you construct it recursively. So you start off with the original array. So this will be a ON operation. You start with the original array of x1, x2, x3, xn, and then you slice it up in half, get the summation of these portions, and then divide and conquer again and again and again. You keep dividing and conquering. So you get a t of n equals to t of n over 2 plus ON solution. So we actually divide and conquer on both, and we get an ON over here. So yeah, this is the time complexity it takes to construct the tree with the recurrence relation. Because we only compute it once. Actually, the merge step is actually O1, because all we need to do is just add the two later. So it's O1, which is O of n, since we have n nodes, which we showed earlier over here. Okay? So the idea of this is that we take the left section, the right section, and we add it up, and that will be our node. So yeah, this is the intuition behind the get sum, the construction of the segment tree. The update follows directly from the get sum. And yeah, you can just combine these now, and then you get log n time complexity for all the operations. So I hope this video makes sense, and I'll leave a link down below with the Geeks for Geeks with the actual code implementation of this. So yeah, I hope you guys enjoyed, and thanks for watching.